Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome back to the deep dive. Grab a comfortable seat, because today we are not just exploring Mars. We're really challenging one of the fundamental assumptions about what the red planet is and what it's capable of.
That's right.
Forget the grandiose images of, ancient flowing rivers or towering volcanoes for a moment, because the biggest discovery this week is microscopic, it's fleeting, and it's highly energetic.
It really is.
Scientists have confirmed with direct observational evidence that Mars is, in fact, sparking.
It's a truly stunning finding, and I think that's the word for it, stunning, because it moves a long-held theoretical puzzle squarely into the realm of observable fact.
Right.
Today, we are deep diving into some crucial analysis. It comes from scientists, primarily those affiliated with the French National Center for Scientific Research, or CNRS, and it was published recently in the journal Nature.
And what a publication.
It details the accidental, and the fact that it was accidental is really key here, the accidental recording of electric discharges on the red planet. Okay, let's unpack this monumental shift. Our mission today is, well, it's complex. First, we need to understand the detective work. Specifically, how these tiny, almost imperceptible sparks were even detected in the first place.
And using an instrument that wasn't even really designed for this task.
Exactly. Then we need to drill down into the fundamental physics. What causes this Martian static, a mechanism known as the triboelectric effect?
And most importantly, and this is the big one, we need to grasp the sheer scope of the implications. This observation is being described as something that, and I'm quoting here, profoundly changes our understanding of the Martian atmosphere.
Profoundly changes? That's not a term scientists use lightly.
Not at all. It's not just some quirky physical measurement. This confirmed electrical activity, it fundamentally alters the planet's chemistry. It forces us to revise our models of atmospheric balance, reconsider our entire approach to searching for ancient life.
And even evaluate the safety risks for any future human exploration.
Seriously, evaluate them, yeah.
And here's where it gets really interesting, connecting that tiny spark to the whole planetary scale. These localized bursts of static energy might actually hold the key to solving one of the most persistent, vexing scientific mysteries on Mars.
The case of the vanishing methane.
The case of the strangely vanishing methane. This deep dive is going to take us from tiny grains of dust and a faint crackle of sound all the way to a global atmospheric overhaul. So let's start with that incredible detective work. The process of finding something you weren't actively looking for. If Mars is sparking, how on Mars did we hear it?
Well, the source material points directly to one innovative piece of technology.
It's
the SuperCam instrument. It's aboard NASA's Perseverance rover, which is, currently exploring the Jezero crater.
SuperCam, we've talked about it before. It's this incredible suite of tools, right? It's got lasers, cameras.
An incredibly sophisticated suite, yes.
Yeah.
For remote sensing, chemical analysis. But for this specific discovery, we are focusing on one component that, until very recently, was entirely novel for planetary exploration.
It's microphone.
It's microphone. This was the first microphone ever successfully operated on the surface of Mars. It started recording shortly after the Perseverance rover landed back in 2021.
So for the first time, we've actually been cataloging the literal sounds of an alien world. I remember hearing those first recordings.
Yeah, it was amazing.
We've heard the wind blowing across those dusty plains, the faint hum of the rover's own mechanisms.
And of course, the rhythmic whirring of the Ingenuity helicopter blades during its revolutionary flights.
Right. So we're talking about over 30 hours of raw Martian acoustics that have been recorded to date. But finding a faint electrical crackle mixed into all of that, that sounds like an incredible feat of data mining.
It is. It's like searching for a single grain of salt on a football field.
Or a needle in a haystack the size of a planet.
Exactly. Mm-hmm. And the location of the detection is paramount to understanding the whole mechanism. The source confirms that the discharges were accidentally recorded right at the center of two Martian dust devils.
Not just anywhere, but inside a dust devil.
Right in the heart of them. And these aren't static landforms. They are the constantly churning, high-speed whirlwinds of fine dust that sweep across the planet. They are essentially localized, high-speed friction generators.
So the dust devil is the necessary mechanical trigger. But how do you, as a scientist sifting through this data, distinguish a faint, high-frequency electrical crackle from the massive amount of noise? I mean, you've got grinding dust, high-speed wind, the general cacophony of a whirlwind sweeping past a microphone. How do you pull that signal out?
That requires extremely sensitive filtering and some very sophisticated analysis. And that's where the teams of dedicated scientists from labs like the Institut de Recherche en Astrophysique et Planétologie and the Laboratoire Atmosphère et Observation Spatiale, that's where they came into play.
So it wasn't just a lucky find, it was a deliberate search through the noise.
A deliberate search. They didn't just hear a random static burst. They confirmed two distinct interlocking physical signatures that proved the electrical discharge was real.
Two signatures. Okay, they're working in tandem. Tell us about those.
Okay, so the first one, and maybe the most obvious, was the electromagnetic signature.
The electricity itself.
The electricity itself, yeah. This is the direct evidence of the burst of current, the electrical component. It's a surge of radio frequency energy caused by the rapid movement of charge. But that alone could be an instrument artifact.
Right. You could have interference.
You could. But what sealed the deal, what confirmed the physical nature of the event, was the simultaneous detection of the acoustic signature.
The actual sound.
Exactly. When an electrical discharge, an arc, jumps through the air, even the thin Martian air, it instantaneously heats the gas in its immediate path.
Like a tiny, super hot filament for a split second.
A perfect analogy. This rapid localized heating causes the air to expand violently, creating a sudden pressure wave. That pressure wave travels outward and, if you are close enough, you hear it as a sharp snap, a crackle, a shock wave.
And the microphone picked up that physical shock wave.
It picked it up.
That is truly phenomenal. So the dual nature of the detection, the electrical signal, combined with its audible consequence, that just removes all doubt.
It really does. It moves the existence of electric discharges in the Martian atmosphere squarely from the theoretical column into the observational column. It validates what physicists have been modeling for decades.
So it's critical to understand the scale here. For anyone listening trying to grasp the sheer force of this event, what are we talking about?
Well, the analysis provides a very, very relatable analogy. We are not talking about the huge, massive, destructive lightning bolts that split the sky during terrestrial thunderstorms.
So no enormous planetary fireworks display?
No, nothing like that. You're not going to see this from orbit. These signals were confirmed to be electric discharges comparable in scale and intensity to the small static electricity shocks you experience right here on Earth.
Ah, okay.
You know, when you shuffle across a carpet and then touch a metal doorknob in dry weather?
I know that shock well, that little snap.
That's the one. The kind of shock that makes you jump, perhaps causes a tiny visible centimeter-long spark, and definitely produces that tiny sharp snapping sound.
That door handle analogy works perfectly for the relative scale. So it's a small, localized event, something you could easily ignore if you weren't specifically listening for it.
Exactly. Yet its presence on another world, confirmed by a microphone, signals something enormous about the entire planetary environment.
The accidental listen of a tiny, terrestrial-sized static shock is the gateway to redefining Martian science.
It really is. The instruments proved that not only is the physics right, but we need to pay very, very close attention to these microscale events. So section 1 was about the how of the accidental detection. This next part is really about the why. The fundamental cause, the specific physics of how ubiquitous Martian dust creates these recurring sparks.
Okay, so why does swirling dust create electricity? And maybe more importantly, why is this process so effective on Mars? What is the core mechanism that turns mechanical friction into electrical potential?
The mechanism is universally known as the triboelectric effect. It's often just simplified to friction electricity.
Triboelectric?
Yeah. So when tiny particles, and Martian dust, or regolith, is famously fine, almost like talcum powder, when they rub against each other vigorously inside those dust devils, this physical friction causes electrons to transfer from the surface of one particle to another.
Okay, so you have this constant process of charge separation. Some particles are gaining a surplus of negative charge electrons, and others are left with a positive charge deficiency.
Exactly. This friction causes massive amounts of charge to be separated and then accumulated within that dust cloud.
Yeah.
The discharge, the spark that happens when the electrical potential difference between the dust cloud and the ground, or maybe between different highly charged regions within the cloud, just becomes too great.
It hits a breaking point.
It hits a breaking point. At that point, the atmosphere simply cannot insulate the 2 points anymore, and the charge releases itself rapidly in the form of an electric arc.
And the source confirms the scale of these arcs. They were only a few centimeters long, but powerful enough locally to generate those audible shock waves we just talked about.
A tiny, focused electrical explosion happening over and over again.
It's a very high-energy miniature event. Now, as the source notes, this effect, this dust charging, it's common even here on Earth. I mean, you see it in desert sandstorms.
Oh yeah, dust particles in arid regions can become highly charged, but
Earth doesn't generally have these pervasive, rapid, static discharge events just from dust devils. Even in massive storms, we get huge lightning bolts, but that's driven by ice and water in thunderclouds, which is a totally different mechanism.
a completely different process.
So why is Mars so much more conducive to these static sparks?
This is the single most crucial piece of physics that makes the Martian environment unique for static discharge. The atmosphere's insulating properties, or, well, the lack thereof. We need to talk about something called dielectric strength.
Dielectric strength? That's the ability of a material, in this case the atmospheric gas, to resist the flow of electricity, to act as an insulator.
Precisely. On Earth, our atmosphere is thick and dense. It's roughly 1,000 times denser than Mars's and is composed mostly of nitrogen and oxygen. This thick, dense mixture acts as a very, very effective insulator. It possesses a high dielectric strength.
So to overcome that insulation and create a spark, let's say a centimeter-long one, like on Mars, you'd need a huge buildup of charge.
An absolutely massive buildup, often tens of thousands of volts per centimeter. The terrestrial atmosphere resists the spark, meaning you need a huge voltage difference for that breakdown to occur.
Okay, so that's Earth. What about Mars?
Well, on Mars, the atmosphere is incredibly thin, less than 1% the density of Earth's at sea level, and it's predominantly made up of carbon dioxide. This critical difference radically changes the equation.
How so?
Because the pressure is so low, the mean free path of electrons is much longer.
Meaning the electrons can travel further before they hit an obstacle like another gas molecule.
Exactly. In thin air, once an electron is freed, it gets accelerated by the electric field and can travel a greater distance. It picks up more kinetic energy before it collides with another gas molecule.
And when it finally does collide,
It has enough energy to ionize that molecule, freeing another electron, which then accelerates, hits another molecule, frees another electron. It leads to a cascade effect. It's known as a runaway breakdown.
and that cascade is what leads directly to the formation of the plasma, the spark itself.
Yes. Because the atmosphere is so tenuous, the resistance to the flow of charge is significantly reduced. The source material states it very clearly. The insulating capacity of the Martian atmosphere is drastically lower. And that means the amount of charge needed to form sparks on Mars is significantly lower than what is required on Earth.
That is a crucial distinction. It's like,
Yeah.
if a terrestrial dust devil occurs, it might generate charge, but the atmosphere acts like a thick rubber glove, containing that charge.
Good analogy.
But if a Martian dust devil occurs, the atmosphere is more like a thin paper layer, which is easily ripped apart by a relatively modest electrical potential difference built up from that same dust friction.
It validates the physics perfectly. The Martian environment is highly conducive to charge separation and discharge during common phenomena like dust devils. It tells us that Martian weather events aren't just mechanical phenomena. They're electrical phenomena, constantly generating these miniature plasma bursts all across the surface.
And understanding that atmospheric breakdown at low pressure is fundamental to everything else we're about to discuss.
Absolutely.
So now we move into the truly profound implications, the consequences that go far beyond physics and land squarely in the realm of planetary chemistry. This is the section that really redefines our view of Mars.
This is the massive takeaway for planetary scientists for sure.
The source material emphasizes this, stating flatly, the discovery of these electrical discharges profoundly changes our understanding of Martian atmospheric chemistry.
And it does. For decades, our atmospheric models treated Mars as a chemically slow world, a world where major atmospheric reactions were driven primarily by solar light, a process we call photochemistry.
Right, sunlight breaking molecules apart.
Exactly. Now, we have direct proof that electricity is acting as a fast, high-energy, and highly destructive chemical agent. This introduces a whole new class of reactions, plasma chemistry.
Okay, so let's define that contrast for everyone. What is photochemistry and why is it considered slow compared to this new electrical process?
Photochemistry relies on high-energy ultraviolet light from the sun breaking apart molecules, mostly in the upper atmosphere. It's efficient at high altitudes, but it's generally slow in generating highly reactive compounds down near the surface. It's a steady, predictable process that governs the basic equilibrium.
And the electric discharge.
The spark, or the microplasma, is the exact opposite. These discharges represent localized bursts of intense transient energy, and that energy is more than sufficient to break apart atmospheric molecules like carbon dioxide and water vapor, which are present in trace amounts, into highly reactive fragments called radicals.
So it's not a slow, steady process. It's a violent, instantaneous one.
A violent one, yes. This process dramatically accelerates the formation of highly oxidizing compounds right at the surface layer.
Okay, so we have a sudden, intense, local chemical factory that's powered by static electricity. And it's capable of generating these chemically destructive compounds that wouldn't normally form so easily in that cold, thin environment.
Precisely. And these highly oxidizing compounds are, by their very nature, chemically ravenous. They readily steal electrons from other molecules, causing them to break apart violently.
So think of them as hyperreactive chemical scavengers, capable of a very rapid atmospheric cleanup.
That's a great way to put it. And the effects of these substances are twofold, both of which have massive implications for Martian science. Let's start with the big one for astrobiology, the search for life.
What's the impact there?
Well, this presents a serious new hurdle. The first major destructive impact is on organic molecules.
The building blocks of life.
The building blocks of life, exactly. And crucially, they are also the relics of past life, what we call biosignatures. The source notes explicitly that these oxidizing substances generated by the sparks can effectively destroy organic molecules that may be preserved on the Martian surface.
Wow. So if Perseverance is drilling for evidence of past microbial life, and the only evidence left is, say, preserved organic carbon deep beneath the surface, these constant, pervasive static sparks could be generating reactive species like superoxides or hydrogen peroxide that leach down and erase that evidence.
It could be erasing the evidence almost as quickly as we search for it. It adds a new layer of difficulty to the search for biosignatures. We already knew Martian soil was chemically aggressive because of UV radiation creating surface oxidizers. Right. But now we know that friction-driven electrical activity is a continuous, rapid, localized generator of even more powerful oxidizers, driving that destruction deeper into the regolith boundary.
And the second major impact is on the overall atmospheric balance. You mentioned this profoundly upsets the photochemical balance. What does that mean in practice?
It means it introduces a rapid, previously unaccounted-for chemical sink. These sparks generate oxidizers that rapidly destroy numerous other compounds that are just floating in the lower atmosphere.
So the whole chemical equilibrium?
The whole thing. How different gases interact and persist, it's being disrupted by these high-energy electrical events. We thought atmospheric decay was governed primarily by slow photochemistry. Now we know fast-acting, high-energy plasma discharges are introducing rapid, unexpected decay mechanisms.
And this rapid decay mechanism, this is the key to solving the big puzzle, isn't it? The methane mystery.
This is the aha moment. This is what ties this new microphysical discovery directly to a high-profile, long-standing scientific debate.
Absolutely. So remind us of the puzzle. It started when previous missions detected pulses of methane gas on Mars.
Right. And methane, or text-to-open force, is important because on Earth, it's often a byproduct of biological activity. It can also be geological, but it's a key molecule. But on Mars, it just doesn't stick around long enough.
Right, because according to the slow photochemical models, that methane should persist for several hundred years before being completely destroyed by solar UV.
Correct. But observations showed it vanishing much, much faster, sometimes within weeks or months. It was a huge anomaly.
A massive discrepancy.
Scientists proposed everything. Specialized subsurface geology, unknown atmospheric dynamics. They were trying to explain the missing methane. It was almost as if there was a secret atmospheric vacuum cleaner working overtime, one that was much more efficient than the sun.
Well, now we have a strong candidate for that vacuum cleaner.
Precisely. The discovery of widespread recurring electrical discharges provides the highly plausible explanation. The highly oxidizing compounds, specifically the oxygen radicals and hydrogen peroxides generated by the static sparks, could be acting as that powerful chemical sink.
They're just eating the methane.
They're rapidly breaking it down in the lower atmosphere, destroying it faster than scientists had previously accounted for in their slow photochemical models. This completely changes the mathematics of atmospheric residence time for key gases.
That is a truly fundamental connection. This discovery doesn't just add a footnote to Martian physics, it solves a high-profile, decade-long anomaly concerning a molecule that is central to the search for life. It tells us the destruction is happening locally, rapidly, and frequently.
And this connects to prior research in a significant way. For years, scientists have been looking for evidence of large-scale electrical activity associated with dust storms. They were looking for something called Schumann resonances.
Okay, for listeners who might not be familiar with that term, what are Schumann resonances?
So Schumann resonances are essentially global electromagnetic waves. They bounce around in the cavity between a planet's surface and the bottom of its ionosphere. On Earth, these resonances are primarily excited by global lightning activity, large, powerful electrical discharges.
So trying to detect them on Mars was an effort to find evidence of massive lightning to confirm planetary electrical activity on a large scale.
Exactly. They were looking for the sound of a bell, the global resonance, but what they found via the SuperCam was the tiny local hammer hitting the surface.
That's a great way to put it.
They were looking for evidence of large, powerful lightning bolts, and instead they found these micro-scale, centimeter-long static sparks happening constantly in dust devils. This confirms the environment is electrically active, and it provides the mechanism, the triboelectric effect, for both the observed small-scale sparks and the hypothesized large-scale effects they were looking for. The tiny sparks are driving global-scale atmospheric changes, and it's a testament to the power of high-energy localized chemistry. So we've established that these static discharges are actively rewriting the chemical landscape of Mars. Now we really have to turn our attention to the physical and practical implications. This involves risks to the Martian climate itself, and crucially, to future robotic and human exploration missions.
Let's start with the climate role. We know dust devils and global dust storms are responsible for churning up and transporting vast amounts of material across the planet. I mean, sometimes blanketing the entire world. How does the electrical charge, this triboelectric charging, influence that large-scale dust movement?
The source material is quite explicit about this. The electrical charges that are required for these discharges are likely to profoundly affect the transport and dynamics of dust on Mars. Particles that are highly charged just behave completely differently than neutral particles.
Okay, explain that difference in behavior. What does a charged dust particle do that a neutral one doesn't?
Well, consider two key effects. First, charged particles exert electrostatic forces on each other. So particles with the same charge will repel. This means the charge buildup can actually help aerosolize the dust, keeping it suspended longer in that thin atmosphere rather than just settling back to the surface.
So it's like they're pushing each other away, keeping the cloud puffed up.
Exactly. And second, charged particles are highly susceptible to electric fields. Even weak fields can levitate charged dust far more easily than gravity or simple wind lift could. This phenomenon is critical for understanding Martian dust mobility.
So the static charge isn't just a byproduct of the dust moving. It fundamentally changes how the dust moves, where it goes, and how long it stays airborne.
Yes, precisely. And since dust transport plays a central role in the Martian climate, it affects atmospheric heating because the particles absorb solar radiation, it affects cloud formation, the entire energy balance. Understanding the dynamics of charged dust is absolutely essential for modeling Martian weather and climate accurately.
And the source says the dynamics of Mars's climate currently remain largely unknown.
And these electrical phenomena are a huge, previously missing piece of that puzzle. We cannot accurately predict dust storms without factoring in the electrical charge and the resulting electrostatic forces.
So beyond climate modeling, this brings us to the immediate practical concerns for mission planners and the existing robotic infrastructure. We're talking about the threat to technology.
Yes, the immediate threat is electrostatic discharge, or ESD, to the sensitive electronic equipment. I mean, just think about your own experience with static electricity. A sudden, powerful shock can destroy a delicate circuit board.
Oh, absolutely.
On Mars, where we now know the atmosphere facilitates breakdown at low voltages, the source explicitly states that these recurring charges could also pose a risk to the electronic equipment of current robotic missions.
So we're talking about highly specialized, multi-million-dollar components, sensors, cameras, critical microprocessors that are operating right in the middle of this static generating environment.
Modern circuitry, especially highly integrated CMOS chips, they're extremely sensitive to voltage spikes. A powerful enough or a poorly grounded static discharge could easily fry the most sensitive electronics on the rover. It could potentially end a mission overnight.
So it's an environmental hazard that engineers now have to rigorously design against. Robust grounding systems, extensive shielding, all of that becomes paramount.
Absolutely. The rover shell, its wheels, its instruments, they all have to be designed to safely dissipate accumulated charge, especially when it's navigating through a highly charged dust devil or during a global dust storm where that charge accumulation would just be massive and continuous.
And the risk only amplifies exponentially when we start talking about sending people. If robots are at risk, what about the flesh and blood of future astronauts?
The source confirms the severity, stating that these discharges constitute a danger to potential future manned missions. The risk extends far beyond just frying electronics. We are looking at a system-level hazard for human infrastructure.
Let's elaborate on those practical human safety implications. Paint a picture for us.
Okay, consider an astronaut walking across the surface on an EVA. Their suit, built of multiple layers of advanced material, will generate a massive triboelectric charge just through movement and friction with the thin air and dust.
So they become large walking capacitors.
That's exactly what they are. If they touch a grounded habitat or a piece of equipment, they could discharge with enough energy to cause serious injury, or, at the very least, destroy critical interfaces and communication gear on their suit.
And the habitat itself is a major concern. If you have an enclosed environment that's pressurized with oxygen, you introduce a serious fire risk.
A huge fire risk. If dust that's adhering to the habitat surface accumulates charge, and a discharge occurs inside a highly oxygenated environment, maybe during an airlock repressurization, or if materials are brought inside, that spark could ignite flammable materials. That could lead to a catastrophic fire or explosion.
So designing Martian habitats, rovers, even the basic materials used for astronaut suits will require intensive engineering dedicated to mitigating this electrostatic discharge risk.
Everything needs to be properly grounded and shielded. The Martian surface, far from being electrically benign, is now confirmed as a high-voltage environment just waiting to shock you and your technology.
And we shouldn't overlook the optical and thermal implications either. If charged dust adheres persistently to solar panels, that reduces power generation.
It's a huge problem.
Or if it sticks to camera lenses and instrument windows, it compromises the entire mission's productivity. Static electricity isn't just a momentary shock, it's a constant operational interference.
That's a crucial detail. Electrostatic attraction is why Mars rovers, historically, have had such difficulty shedding fine dust from solar panels. The electrical field holds the dust tightly. Understanding and neutralizing the charge is paramount not only for protecting circuitry, but also for maintaining power generation and sensory perception over multi-year missions. The entire concept of surface operations must now integrate pervasive static management.
For our penultimate section, I want to step back and look at the methodology itself, because this deep dive is a stunning testament to the power of one single instrument, the SuperCam microphone. This isn't just a successful piece of tech, it's a revolutionary tool for planetary science. It's a whole new sensory capability.
It absolutely is, and it really heralds a paradigm shift. Up until this discovery, planetary exploration was overwhelmingly dominated by visual imaging, seismology, and direct chemical analysis.
Right, what we can see or touch.
Exactly. Acoustics was arguably seen as an ancillary measurement. A nice addition for capturing wind speed or the novelty of hearing a helicopter on another planet.
But this observation, alongside those clear recordings of the wind and the Ingenuity helicopter flights, it confirms the enormous potential of acoustics as a tool for planetary exploration. It validates the idea that we need to stop just looking and start listening very closely to other worlds to detect phenomena that are otherwise invisible.
The value here lies in capturing non-visible, non-seismic, yet highly significant physical phenomena. We can't visually detect the electric charge buildup, but we can detect its sudden, powerful acoustic release. This fundamentally broadens the sensory bandwidth we use to analyze an alien environment.
So a microphone provides unique access to fluid dynamics and plasma physics that traditional sensors might just miss.
That's right. And the beauty of this specific detection lies in the fact that we got two different confirmations for the price of one. We got the electromagnetic signal of the arc itself, and the acoustic signature of the resulting shock wave traveling through the thin atmosphere.
That dual detection is fundamentally powerful for scientific validation, isn't it?
Incredibly powerful. The acoustic signature provides a time reference and a confirmation of the physical interaction with the atmospheric gas. It confirms the presence and timing of that high-frequency electromagnetic event. This redundancy, using two entirely different physical principles, EM radiation and sound pressure waves, to confirm the exact same phenomenon, massively increases the data reliability and our confidence in the finding.
So the microphone is acting as an indispensable secondary sensor, a cross-check for the electrical environment.
Exactly. And if we think about future applications, it opens the door for dedicated acoustic monitoring. We can now design next-generation missions where our primary objective is to map the frequency, intensity, and location of these electrical events across the entire planet simply by listening.
So if we want to know where the most destructive rapid chemistry is occurring, we don't need expensive spectrometers everywhere. We just have to follow the sounds of the crackling static.
In a sense, yes. It shifts the paradigm entirely. Instead of simply trying to sample the chemistry and figuring out why it's changing slowly, we can use acoustics to pinpoint the precise location of the rapid, destructive chemical drivers.
And what else could we be listening for?
Oh, the applications are enormous. Beyond static electricity, acoustics could be used to detect the faint impacts of micrometeorites, providing real-time flux measurements. It could potentially detect seismic activity with higher fidelity in certain environments, or even monitor thermal processes, like the sound of rock expansion or contraction as temperatures swing dramatically between Martian day and night.
It's a completely untapped resource.
It is. This observation has proven that sound is not just an ancillary measurement of wind speed. It's a critical observational tool for understanding planetary physics and atmospheric chemistry. We learned to listen to Mars, and in return, Mars revealed an electrically active dimension we thought was dormant.
This has been a truly comprehensive journey into the unexpected world of Martian static electricity. To quickly recap the monumental findings from this deep dive, we confirmed that tiny, centimeter-long static electricity sparks are a physical reality on Mars, and they were accidentally detected by the SuperCam microphone right at the center of churning dust devils.
We established that the extremely thin, carbon dioxide-rich Martian atmosphere is the crucial difference from Earth. It drastically reduces the dielectric strength and lowers the charge needed to create these frequent triboelectric discharges. These discharges, in turn, generate powerful, highly oxidizing compounds through plasma chemistry, introducing a rapid chemical sink.
And most dramatically, this gives us a strong, plausible, and physically validated explanation for that long-standing scientific puzzle of the surprisingly rapid disappearance of atmospheric methane. The highly oxidizing compounds created by the static are likely acting as the missing hyper-efficient chemical sink, destroying organic molecules both in the atmosphere and potentially on the surface.
Finally, we highlighted the critical practical risks. This newly confirmed electrical activity complicates climate modeling by affecting dust transport dynamics. It poses an immediate risk of electrostatic discharge damage to current robotic electronic equipment, and it fundamentally constitutes a danger to potential future manned missions, requiring intensive protective engineering for habitats and astronaut suits.
The sources demonstrate unequivocally that Mars, which was previously viewed as a chemically slow and electrically passive world driven mainly by solar radiation, is actually an environment where constant mechanical friction, the ubiquitous movement of fine dust, is a powerful and active driver of rapid destructive chemical change.
It's a planet that is constantly chewing up its own chemical history.
Exactly, which leaves us with a truly provocative thought for you to carry forward.
If these tiny centimeter-long sparks, which required a high-tech microphone to even detect, can fundamentally destroy organic molecules on the surface and rapidly shift the global atmospheric balance of an entire planet. What other previously undetected small-scale physical processes are drastically influencing planetary environments across our solar system?
Are there similar silent destructive mechanisms at work on other airless bodies or in deep, dusty atmospheres that we have simply failed to listen for?
The spark on Mars reminds us that sometimes the most profound forces in planetary science are the ones we can barely hear, proving that discovery often requires us to introduce entirely new senses to the cosmos.